Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments, and we're in part 2 of an 11-part mini-series within that larger playlist. This mini-series deals with hierarchical designs, and in this video we're going to look at the column spaces of that design matrix. So in part 1 we introduced a model of y is equal to x star beta star plus epsilon, so it's a linear model. We partitioned it into, a column of ones, x alpha times alpha, and this deals with factor A, and then x beta times beta, this deals with factor B. And factor B is nested within factor A, plus epsilon. And this is normally distributed. So if we look at the column spaces, we're going to let J be the perpendicular projection matrix onto the column space of ones. And this is how you define a perpendicular projection matrix. So if you take J times Y, then this piece here becomes this piece, and we have Y. And the reason, and U is a matrix of all ones with size AB by N. Now if there's a number or an index up here, then it's not a square matrix. But if there's only one index, then U represents a matrix of all ones. So when you take this vector and add it, all ones, so you're adding up every one of those, and then you divide by how many there are, you get the grand mean. And that's for every row. So you can just factor out that grand mean value, and it's times a one vector. And they call this the grand mean vector, GM. Now, M alpha defined as, X alpha times X alpha transpose, X alpha inverse, X alpha transpose. That's going to be the perpendicular projection matrix onto the column space of X alpha. Now, to get some structure on this, if we just look at this piece here, that creates an identity matrix times Bn. Now the inverse of that is just 1 over I, 1 over Bn times I, but the I kind of goes away. Then when you multiply this out, you get a block diagonal matrix of 1 over Bn's, or a matrix of all ones times 1 over Bn. Then when you do this multiplication of M alpha times Y, you get a unique structure. And we call that the alpha mean vector, or the factor A mean vector. And it's essentially the mean for, level 1. So, and then times a one vector of length Bn. Then it's the mean of, for level 2 of factor A, times this one vector all the way down to the 8th level of factor A, the mean, and then times that vector. Now let M beta be, defined like this, and it's the perpendicular projection matrix on the column space of X beta. And to look at some structure, if we look at this here, it's N times I, and we take the inverse, so it's 1 over N times I. So the I kind of goes away, and then we're left with X beta times X beta transpose. And then the structure of this is block diagonal with 1 over N times the matrix of all ones. And when you pre-multiply the Y vector by M beta, you get a mean vector. And sometimes they call it Y beta and then in parentheses alpha. So it's the mean for factor B, but as a reminder, it's nested within, factor A. So it's the mean of 1, 1 times one vector of length 1, the mean of 1, 2 times a vector of length, a one vector of length N, all the way down for every combination until we get to YAA, the mean of, that little cell YAA, times a vector of all ones of length N. Now, to give a little more detail on what we just did, is notice that the one vector is a part of the column space of X alpha. Or you can think of the column space of 1 is a subspace of the column space of X alpha. Now, this matrix, M alpha minus J, so remember those are both perpendicular projection matrices, and since J, projects onto this as a subset of X alpha, which is, this projects onto, the difference is a perpendicular projection matrix orthogonal to the 1 vector with respect to the column space of X alpha. So what that means is if you pre-multiply some dangling vector times this, it's going to shove it into the column space of X alpha, but orthogonal to the 1 vector. And how we do that is we take the column space of X alpha, which is actually this, it's equal to this. If we just add a vector of all ones, this is redundant, so it's the same column space. But then we use the Graham-Smith theorem, our algorithm, to make these columns orthogonal to the 1 vector. Then, since these are orthogonal spaces, the perpendicular projection matrix onto this is just the addition of those 2 vectors. Well, this is the projection matrix onto 1s is J. Projection matrices onto X alpha orthogonal to 1 is this vector. So we add those and we get M alpha. But that's what we're saying it should be to begin with. So it's on to X alpha. Now X alpha, the column space of X alpha is a subset of the column space of X beta. And so if we subtract their perpendicular projection matrices, so M beta minus M alpha, it's the perpendicular projection matrix onto the orthogonal complement space of X alpha with respect to X beta. So if we pre-multiply some vector times this, it's going to shove that vector into the column space of X beta, but orthogonal to X alpha. So if we look at the whole column space, so the column space of X star, we partition it, this is what X star is. Then we use the Graham-Smith theorem to make these columns orthogonal to 1, and then we make X beta orthogonal to 1, and then by default we kind of get that it's orthogonal to X alpha star. And so all these subspaces are orthogonal. So the perpendicular projection matrix onto this column space of X star is actually the addition of those 3 perpendicular projection matrices. So, but if we just look at M, the perpendicular projection matrix on the column space of X star, you take X star transpose X star generalized inverse, because this is singular, times X transpose, X star transpose, that should be a transpose. And that's the perpendicular projection matrix on the column space of X star. But if we use what we know about perpendicular projection matrices, M should be equal to J, M alpha minus J, and then this space is actually orthogonal to that, which we said was M beta minus M alpha. So, that cancels with this, M alphas cancels, and it just leaves M beta. So M is actually equal to the perpendicular projection matrix on the column space of betas. They're the same space. So what that tells us is the column space of 1s is a subset of the column space of alpha, which is a subset of the column space of beta, which is equal to the column space of X star. All right, well, that's all I have for column spaces of this design matrix. Hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.